cooling our body. Why does that work? How much energy does it take to evaporate water? A lot. So if you put a lot of water on your skin, you think maybe it's got to get that energy from somewhere? Now, I'm not telling you that it takes this much energy to evaporate water off of your skin, because once again, entropy plays a role here. We're not bringing entropy into the equation yet. But conceptually, that is why we sweat. We sweat because evaporating water takes a lot of energy. And if we can find a way to use that energy needed to suck some of that energy from your body, then that will help cool you off. That is also where we get things like, what is the term? Heat index, right? It's going to be 96 degrees tomorrow with a heat index of 108. What's that mean? It means don't be an idiot, don't go outside and get all sweaty. When the humidity is really high, there's no place for the water on your skin to go. It can't evaporate. And so therefore it can't cool you off. This is why 108 degrees or 95 degrees with high humidity feels like 108. That's what that heat index is. You will heat up and react as if it was 108 degrees instead of the 95 that it is, because the humidity is so high that your normal sweating mechanism to cool you off, all it will do is get your shirt wet. And that has everything to do with how much energy it takes to change the state of water. And a few other things too. So here we have heat of vaporization, conversion factors. We can calculate how much heat it takes to do something. Do you feel some math coming? Look at this curve. Down here is heat added. So this is, let's take some water at negative 40 degrees and start adding heat. That temperature is going to rise all the way to 0, but then for a certain amount of time, the temperature will not change. What is happening? We're still adding heat every second, but the temperature is not changing. What is happening instead? Where is that heat going? It's paying for a change of state, right? Then once we're all liquid, we can rise from 0 to 100 in a relative linear line. But then for a significant period of time, we keep adding the same amount of energy, but nothing is happening to our temperature. What is happening? We are paying for the change of state from liquid to gas. And once we're all gas, then we can start raising in temperature again. Could you tell me how much energy that was? Yes. Short answer is a lot. You are correct. But if I said that you've got, say, 50 grams of ice at negative 40 degrees C, how much energy would it take to turn it into 50 grams of gas at 160 degrees C? Could you do that? What would it take? We would need specific heat calculations here, right? Warming it up to 0. Then we would need the heat of fusion calculations to melt it. Then we would need specific heat calculations to raise the temperature to 100. Then we would need the evaporation or the boiling calculations to turn it all into a gas. Then we would need specific heat calculations to raise the temperature of the gas. Could you do all of those things? Eventually. It would take you a while. But you could do them, right? There's nothing... When you break it down into those steps, we've done all of those things, right? And if you had, say, a relatively unlimited amount of time on a homework assignment, or, say, a slightly more limited amount of time on an exam, some of that could be done, right? No? It's just too much. Too much effort shutting off. The cooling curve, it's exactly the same but in the reverse direction. Why? It's a very simple answer. But it seems almost counterintuitive. The physical and chemical properties of matter are directly dependent upon the atoms that make them up. And therefore, the amount of energy it takes to go in this direction is exactly the same as the amount of energy you get back going in this direction. It's exactly the same.
Well, but then with this, what's the word? Sublimation or whatever?
Mm-hmm.
How does it skip?
That is a really good question. So how does it go from a solid to a gas with no change in temperature? It's a really good question. And what I will tell you is it takes exactly the same amount of energy.
Okay, so that's what you're talking about right now, is energy.
Right. There's a guy that's hiding behind this graph. And he's like twisting his mustache with an evil grin and laughing maniacally because he has these nefarious plots.
Is this the guy from the Pink Panther? Is that what it is?
No, this guy's called Entropy.
Okay.
But he could be wearing a superhero villain suit if you like. Entropy is a huge part of these calculations.
Oh, so that's what you were talking about earlier.
Yes. It is a huge part of these calculations that we're not going to worry so much about right now.
Thank you.
Because you don't need to get that. And let's put it this way. It's hard enough to really conceptualize how understanding how the specific heat of water is going to impact your day-to-day life as a medical professional. Adding in calculations for entropy just makes it almost like arguing about philosophy. It's like, yeah, this is even more pointless. Like, it's a fundamental thing. I don't mean to downplay entropy or badmouth them. Entropy is as important, if not more important, than freaking gravity when it comes to really understanding how some of this stuff works. But we don't need to get that detailed.
I'm totally fine with that.
Okay, good. I thought you might be. Now, that's not to say that he's not going to come in later, but we're not going to worry about him right now.
Okay, we don't have to wrap it in by then if we don't want to.
And that's it. Here I was worried I wasn't going to finish. Are we supposed to go to 8:55? We have 5 minutes. Anybody have any questions about what we went over today? Sorry if that last little bit felt a little rushed. I didn't want to leave anything behind, but like I said, it's all math, but we'd already done it all, right? We've done specific heat calculations. We've done melting calculations. Plus, it didn't actually ask us to do math. I'm pretty sure if we look into those problems, the problem set, there are some questions in there that would walk you through all of that, like doing this first and adding this. I highly suggest you check it out. I'm going to try and make sure that I get your homework posted so it'll open up tomorrow. It will be due, I guess the easiest way to do it is just make it due before class starts a week from today.
What time
So,
are you going to open that up tomorrow?
I'll probably set it to open up at 8 o'clock. If I finish it tonight, I'll time it to open up at 8 tomorrow, 8 a.m.
For the questions, for the problem.
Which is what I'll do for the test too.
I won't have kids home.
For like the problem questions that you have as extras and
Right.
the homework, is that similar on what the test will look like?
That is a really good question. So here's what I can tell you for that. I haven't put the test together yet. What I can tell you is there's a difference between the way that the book, because the homework problems are going to either be exactly or very similar to what's in the back of your book. So if you notice, the back of your book, half of those problems have answers, and half of them don't. So your homework is going to come from the half that don't. But that means that there are problems exactly like them that do have answers worked out, so you can practice a little bit. It also means that if you're a really, really motivated student, you could get ahead on your homework and just answer all of the questions at the end of every chapter so that you're just ready to pick that answer and go. I don't expect anybody to do that, but I'm just saying you could if you want to. So the test, on the other hand, is going to be different because what I'm not going to do is go back through and manually grade
48 questions from 10 students, possibly more than 10 students if this is during a regular session when I had more like 20 or 30 students in here. So those questions are going to be similar, but they're probably going to be like true-false questions or multiple choice questions. So you'll still have to do math very similar to those, but it'll be like pick the correct answer out of 4 options. Or it'll be like, for example, do this math, true, false. This, this would heat up faster than water, right? So like you have to do the math, and then I can ask you a true, false question to determine whether or not you understand the relationship between specific gravity of A and B, right? Questions like that.
But I'm more so, I mean, that's helpful to know, but even on a level of difficulty, like, will they be in line? I only ask because I had a horrible experience with a teacher that put their tests on D2L and take on your own. I think because they thought we could take it on our own, they
made it really, really hard?
Really, really hard.
A really, really hard test is the type of thing we do because A, you can take it anytime you want, and were those timed?
Yes.
They were timed too?
They were terrible.
Yeah, I can see where that might be bad. Like if I was going to do that, I wouldn't put a time limit on it. Like this is going to take you 6 hours to finish, but suck it up, you'll have your book, so don't complain. Like I could maybe see that as a mentality, but no, some of the questions will be harder, yes. And unfortunately, because of the nature of a random block test, if you're helping a friend, your question might have 2 or 3 or 4 questions and like, wow, these were kind of like tough. And your friend's test was like, whoa, mine were all easy. But then the next time you do it, they might get shafted with the hard questions and yours the easy one. So the test bank questions are going to have some easy questions in them, and they're going to have some hard questions in them. And it will be random which ones you see. So your test might be a little harder or a little easier than somebody else's. But no, the intention is to make a test that I think a reasonable student would be able to finish in a reasonable amount of time, that being less than 2 hours. So I'm not going to give you 5 problems that work out 50 grams from -40 to 160, right? But there might be something in there where you're doing a step or 2 of that, or it might be you're doing the first half and somebody else is doing the last half, and that type of thing. Or if you're really unlucky, one question where you're doing the first half, and another question where you're doing the last half, and then you end up doing it all anyway. But hey, it's 2 of your questions instead of just 1.
So just to be sure with the homework though, is it going to be from the book, or is it going to be some questions that you're like, yep, you guys can answer that?
They're going to be,
throw that in there.
9 out of 10 are going to be from the book.
Okay.
If they're different, it's going to be something that, for example, something that I was trying to decide what to do. I wanted to have, there's some questions from chapter 2 that are about rounding to significant figures. And there's a couple of little like, do you really understand this or are you guessing type of things.
Right.
And unfortunately, none of the homework problems had one of those examples. And so I was like, well, I could just, never mind. So I didn't have that. But there might be a situation where it's like that. It was like, well, really, I want to use this number type of thing. And so it might not be exactly there. But 9 times out of 10, it's going to be straight out of the back of your chapter. I'm not trying to make this any more harder on me than I am on you. So, like, this homework is there to force you to do a little bit of out-of-class application, and also to give you a little bit of grade padding in case you maybe don't do so hot on one of your exams.
Do you ever curve?
No,
Okay.
nor would you want me to if I actually curved the way a curve should work. Like Harvard curve, when people say, do you curve your class? The short answer is yes, the class is already curved. 425 points out of 500 is an A.
Yeah.
That's a curve.
I'll take it.
Right.
Okay.
The long end, the reason why, like, when students ask for a curve, you don't want a curve. Like, the way it used to be, and I had a professor who tried to sort of apply this, was a curve meant that no matter what everybody's grades were, you could get a 36% out of all of the points in the class. And if you were the highest one in the class, you got an A. And if there were 30 students in the class, you and 3 other people got an A. And then 10 people got a B, or excuse me, 5 or 6 people got a B. And then about 15 people got a C.
So bell curve.
It was a bell curve. And so, but the thing was, is that when you do that, like, I failed every test! It's like, yeah, but you're the best student I have. You suck! Like, who would want to be a teacher getting a 36% in a class? I had that happen to me when I was getting my PhD. And the teacher's like, oh, don't worry, you're fine. Like, I don't care what you say. I've seen my tests. But the problem was is that he wasn't testing what he was teaching. He was just testing, and then like, well, the best ones get an A. Like that, I hate that. It does nothing for students. All it does is create stress for students if they don't understand the way their grade is working. And then the alternative is, let's say everybody's getting 80% plus. If you were curving, that still meant 10% of the class is failing. How would you like to get an 80% and get an F? Right? So, no, I do not curve.
Okay.
But I'm not trying to give bad grades, so.
Oh, you need that one person to show a person in the class.
Right, and then you get the one who's breaking the curve and somebody like kneecaps him on the 4th test.
I like your card. I like your card.
The next chapters are what, 4 and 5?
I'm pretty sure it's, yeah, 4 and 5. There's one